All right, boys and girls, Mr. DeMail here. Just wanted to clarify something before our test on Friday. Problem sets are up and in IPASS, and generally they're very good, but there was one glaring error that I needed to point out. Maybe I had miscommunicated the directions to you, but whenever there is an algebraic way of dealing with a limit, you should be going that way. You should not be trying to substitute in values and look at ratios. So in particular, on the problem set, numbers 27 and 28 seem to be the most commonly abused, I guess is maybe the word, problem, where I didn't take the points off. I probably should have taken points off when looking at people's work. But I often saw a lot of things that look like this. The limit as x approaches 7 from the left of 7 minus x over the absolute value of x minus 7. And people substituted values in and thus came up with an answer of 1 because the ratios constantly came out as the same equal number in the numerator and the denominator, which is all fine and dandy, but not the way in which you should be going about this particular problem. When you deal with absolute value graphs and their ratios, you have to consider the piecewise pieces that make them up. And the way in which you should really be attacking this problem is leaving the numerator as 7 minus x, but considering what piece of the absolute value graph you're on when you are approaching 7 from the left. When you are approaching 7 from the left, we see over here, as the example shows, you're going to be less than 7, which means that you need the absolute value to make the value positive. So we need to use the expression for the absolute value of x minus 7 that yields the positive values when you are approaching 7 from the left. One way in which we can write that is, say, take the opposite of x minus 7. Another way in which we can write that is to say that the opposite of x minus 7, distribute the negative through, is 7 minus x. Therefore, you get the cancellation that you need, and you get that regardless of what's happening, if you're on the piece that is yielding negative values, the limit will approach 1. And if you want to clarify that to yourself, go ahead and take a look at the graph of 7 minus x over the absolute value of x minus 7, and you'll see that for all values to the left of 7, the limit is always going to be 1. It's a horizontal line. When you come in from 7 on the right, you get something different. It goes to negative 1, so you kind of get a graph that looks like if this is 7, if you're coming in from the left, you're positive 1, and then if you're coming in from the right, you're negative 1. So your graph kind of looks like this, and it is not defined at 7, so it's open at both of those. To show you another one, let me just jump to another page. All right, here was the second example. This was number 28. You're looking at the limit as x approaches 1 from the left of 1 minus x squared over the absolute value of 1 minus x. And again, you want to take into consideration getting close to, but not actually getting to 1 from the left. Well, approaching 1 from the left, in the denominator, plugging in values of x that are less than 1 yields positive values. So essentially the absolute value is useless at that point. So when you go ahead, you're going to say that this is really the same as 1 over x, 1 minus x squared over 1 minus x. The numerator factors to 1 minus x, 1 plus x, difference of squares, over 1 minus x. And again, algebraically now we see the 1 minus x's cancel, and all you're concerned with is looking at the limit as x approaches 1 from the left of 1 plus x. And that is a nice direct substitution problem. The answer is 2. What I don't want to see is a string of values plugged in for x and showing that the ratio is starting to approach 2. A, time-wise, I really don't want you wasting your time plugging values in. And B, piecewise functions are going to be critical throughout the year, so being able to split the absolute value into its pieces, being able to know when to use them, and then using the limit laws or the limit rules that apply. So please, if you see something like this on the test on Friday, do it out this way. Obviously, for multiple choice, it's either right or wrong, so I'm not going to be able to stop you from plugging in values, but it's kind of not the best way of going about mathematics for the rest of the year. You don't always want to be trying values and seeing what happens. All right. Thank you for your time. I will see you on Friday. Make sure you stop by tomorrow and pick up your problem sets. See you then. Bye.